Good morning, and thank you for the opportunity to speak today. My talk is about how we can move from millisecond resolved MEG signals to individualized language map that are useful in patients with epilepsy. The central question is not simply whether we can produce a brain map, but whether that map can be made reliable enough to contribute to clinical decision making. I'll begin with individualized language mapping methods um, in epilepsy surgery and briefly review what um, MEG measures. I'll then focus on evoked and induced responses, particularly beta band desynchronization and how use this signal to map language network. From there, I'll discuss the methodological choices that affects laterality and finally how MEG compares with fMRI and how we interpret concordant and discordant cases. The goal of epilepsy surgery is not only seizure control, but preservation of function. Language is particularly challenging because the network is distributed, varies considerably between individuals, and may recognize in epilepsy. Resection involving language-related cortex can lead to persistent naming and communication deficits. And following dominant temporal lobe epilepsy, post-operative naming decline remains an important risk. So our clinical goal is to determine hemispheric dominance while also characterizing the broader distributed language network before resection. Imaging measures the weak magnetic field generated by synchronized cortical currents. These fields are recorded non-invasively by sensors around the head, giving us millisecond temporal resolution. The sensor measurements themselves do not tell us where activity originates, so we combine them with individual anatomy and forward model to reconstruct cortical sources. So this is how we move from tiny neural current to individualized functional brain maps. Once we have the MEG signals, we can extract task-related information into complementary ways. Evoked responses are consistently phase-locked to an event, so averaging enhances reproducible activity and its timing. Induced oscillations are also task-related, but their phase can vary across trials, so conventional averaging may attenuate them. Instead, we measure changes in time frequency power. These two approaches therefore provide complementary information about the language processing. Why focusing on beta band? Beta power decreases when cortical networks become engaged. This phenomenon was first characterized extensively in motor systems, but similar modulation is also seen during cognitive and language processing. Because induced beta activity does not need to remain phase-locked across trial, it can reveal distributed network engagement. MEG source modeling can then allow us to localize those beta changes across different part of the brain, including frontal, temporal, and parietal regions. The clinical question is whether that signal can provide a reliable, individualized estimate of language dominance. Our first clinical application used two overt language production tasks. In auditory description naming, patient heard a description, identified the concept, and produced the target word. In picture naming, they recognized an object and said its name. Although the sensory input differs, both tasks converge on shared stages of word retrieval and speech production. This allowed us to test whether beta modulation could provide consistent language mapping across two clinically feasible production paradigms. Both tests showed sustained beta suppression following stimulus onset. Importantly, when we aligned the analysis to speech onset, beta suppression was also clearly present leading up to the vocal response. So, despite the different task input and variability in response timing, both paradigms showed a similar beta band modulation across the language production period. At the source level, the two naming tasks produced overlapping patterns of beta suppression across distributed language-related cortex. Laterality was also strongly related across tasks, with a correlation of about 0.74. Auditory description naming classified 27 of 29 patients as left lateralized, and picture naming lateralized 24 of 29. So the initial study suggested that beta-based lateralization was reasonably consistent across different production tasks. That led us to the next question. What makes this laterality estimate reliable? We focus on three choices. First is to task contrast baseline versus the match control. Second is the timing because the optimal response may differ across regions and patient. And third is how laterality itself is calculated. We therefore compared magnitude-based, vertex count, and bootstrapping approaches. We addressed this question in a larger cohort of 74 adults with drug-resistant epilepsy. For MEG, semantic decision was contrasted with visual symbol matching. For fMRI, the corresponding clinical paradigm used auditory semantic decision contrasted with tone decision. Both involve the same central semantic judgment and a manual response, but the sensory modality and control task differ. So those differences are important when we later interpret MEG fMRI agreement and discordant. The group map show that the beta response evolves substantially over time. Relative to baseline, the earlier activity is relatively bilateral and contains a strong visual component. Around 450 millisecond, left temporal and inferior frontal engagement begins to emerge, with a strongest lateralization around 600 to 900 millisecond. When we subtract symbol matching, the language response becomes clear and more strongly lateralized because shared sensory and response related activity is reduced. The time-resolved analysis also showed that the optimal lateralization window differs by region. With semantic decision relative to baseline, the peak are broad and MEG fMRI LI correlation reaches about 0.41. With symbol matching contrast, the peak becomes sharper and the relationship with fMRI became stronger, reaching about 0.65 in the lateral language RI. So the match control improves not only spatial specificity, but also the timing and the cross-modal relationship of the laterality estimate. A fixed time window also assumes that every patient processes the task at the same speed, which is clearly not the case. Here, the beta laterality peak in the lateral RI varied substantially across patients, from roughly 350 millisecond to 1.5 second. So we therefore centered a 300 millisecond analysis window on each participant's strongest response. And this accommodates individual temporal variability and provide an additional refinement beyond using a single group defined window. When we combine contrast choice, timing strategy, and laterality method, the dominant effect is the task contrast. Semantic decision relative to symbol matching consistently produce better concordance than semantic decision relative to baseline. Patient-specific timing provide an additional improvement. In the lateral ROI, the best result reaches 90.2% using matched contrast, individualized timing, and the bootstrap laterality index. Overall, 67 of 74 patients were classified concordantly, corresponding to 90.5% agreement of a kappa of 0.81. The 7 grossly discordant cases were not small differences around a threshold. There were true cross-hemispheric reversals. Five were fMRI left and MEG right, and the two showed the opposite pattern. These cases are therefore particularly interesting because the disagreement may reflect task performance, timing, signal quality, differences in physiology, and genuine network reorganization. So there are four messages. First, beta band MEG can provide a reliable estimate of language laterality in a large epilepsy cohort. Second, reliability depends strongly on methodological choices, particularly match control condition, timing, and a robust laterality method. Third, MEG reveals the temporal organization of the language network with different regions become maximally lateralized at different time. And finally, this method can provide individualized and interpretable results that complement fMRI in broader surgical evaluation. In conclusion, beta band MEG provide a non-invasive and time-resolved approach to language lateralization. In this cohort, an optimized analysis pipeline achieved a 90.5% concordance with fMRI. Importantly, the reliability of the result depends on methodological choices, particularly the task contrast, the timing uh, of the analysis, and how laterality is quantified. MEG and fMRI should therefore be viewed as complementary rather competing modality, and discordant cases can themselves be informative. Ultimately, the goal is to provide individualized and interpretable functional map that provides safer presurgical decision making. An important part of translation is making the analysis reproducible and accessible beyond research scripts. We therefore implemented the laterality workflow as MELab with Brainstorm. The user can select the atlas timing strategy and laterality method, and the pipeline generate regional time resolved laterality estimates together with confidence information. The aim is to translate methodological validation into a standardized and interpretable workflow for individualized MEG language mapping. I'd like to thank our patient and families and Medical College of Wisconsin in Milwaukee and Frederick Hospital MEG team, the Epilepsy Connectome Project investigator, our clinical collaborator, and our funding partners. Thank you very much for your attention.